So you might be considering maybe there's better options for filling space, and of course we've got other options. So other cubic structure options are the body-centered cubic option. So it's a bit of an extension of the simple cubic structure where we simply just expand the atoms that were at the corners to accommodate a central atom in the body, in the middle of the cube. Okay, so we see that in here where now there very clearly is a center located, or a body-centered sphere in this cube, and we still have atoms at each of the 8 corners. So hopefully based on the previous exercise, you learned that we had 1 atom per unit cell in simple cubic. We've installed a second, so that's going to give us 2 atoms per unit cell by shifting to the body-centered cubic option. Okay. We could ask, what is the coordination number for this material? And so we can kind of think about that body-centered atom and how many atoms are contacting it. And as you might be able to tell from the diagram, there's contacts along from the center point out to each corner. So we're contacting each of the atoms along the way. And so instead of having a coordination number of 6 like we had in simple cubic, we've increased that now and now have a coordination number of 8 in the body-centered cubic option. That's a bit easier to recognize here with a diagram that's sort of removed the edges of our unit cell, and you can see those corner atoms contacting the body-centered atom here, shown in red this time, and you can see those 8 atoms coordinating to that central atom. Okay, coordination number of 8, and we have 2 atoms per unit cell in this case. Another option is now where we install atoms at the faces and at the center of the faces of each plane of the cube. So again, we've kept our atoms at the corners. So 8/8 of an atom at each of the corners of our cube. And now we've put a half a sphere at each face of the unit cell. So we saw before 8 corners, 1/8 of an atom at each. This time we've got 6 faces to the cube, and so we're going to put a half atom at each. So 6 faces and a half atom at each gives us this piece. And so that total is going to be 3 atoms from the faces and 1 atom from the total of the corners. So we're going to get 4 atoms in the unit cell by a face-centered cubic structure. Drawing the justification of a coordination number is a little bit more difficult here. So again, to make things more simple, we've tried to show 1 atom and all its nearest contact point neighbors, and the outcome here is 12. So there are 12 nearest neighbors of the same atom type that are contacting, and our coordination number is therefore 12. Okay, so with many of those systems, those cubic systems, body-centered cubic, face-centered cubic, we've already been able to explain many of the crystals and the crystal structures that exist for many elements from the periodic table. On the inside of many textbooks, in this case, the inside of Callister's textbook, you can see here that we've got the crystal structure described, and we here see that aluminum, for example, can adopt a face-centered cubic lattice at standard temperature and pressure of 20 degrees C, and a body-centered cubic option can describe barium, and we see a lot of other materials explained by those cubic systems. The rhombohedral option was one of our other lattices that we saw in our 7 options. And we see some others here described by a hexagonal system. And we'll spend some time on the hexagonal system next. Okay. So as just to review, we've covered the cubic systems. These make up 3 of the 14 crystal lattices, or Bravais lattices, that are all the possibilities for installing atoms in our 7 crystal systems. Okay, so we've just described 3 of the 14 Bravais lattices. The tetragonal option was where we were allowing one of the edge lengths to be a little bit longer or shorter than the other 2. And here we have a similar idea. We could have a simple tetragonal system, or we could body center an atom. It's known that the face-centered tetragonal system is not found, and so it's not one of the Bravais lattices known. And so you see similar options here as you go through the other 7 types of crystal structures. And so here are the orthorhombics. We have simple, body-centered, and base-centered, this time as options. Okay, so 2 of the faces have been occupied by atoms in the base-centered orthorhombic. And even we now get to see the face-centered orthorhombic as well. Okay, and then rhombohedral, we only see atoms at each of the corners of that crystal structure. And hexagonal is, as you can tell, similar to our cubic system here, and we'll spend a little bit more time on that, seeing how that's unique and related to, for example, the face-centered cubic lattice in a moment. Okay, to put that in a different way, just to give you a sense here, we've seen the 7 crystal systems shown in this column, and we can show that there are 14 crystal lattices that can be established thereafter, 3 of which are in the cubic crystal system, 2 can be in the tetragonal, and there's only 1 in the hexagonal that we'll see. Orthorhombic, we saw 4, with the difference here in the most atom-rich unit cells being a face-centered versus a base-centered option. And monoclinic, we have 2 options there, and then trigonal and rhombohedral, 2 options for the Bravais lattices there. Okay, so on to the hexagonal close pack structure, HCP. The idea here is to first show and use planes of atoms that are as dense as possible. So here we've asked the atoms to pack in a plane as dense as possible, and that is going to give us hexagonal close packing. Looks a bit like a honeycomb in its default structure, based on at least 7 atoms located in that hexagon, 1 centered on that hexagon. And as we extend that, we establish a plane of atoms that are hexagonally close packed. Okay, so that could be one of the bases of the hexagonal unit cell. And we see that shown down there, shown here at the top, and giving us one of those planes that extend past the simplest unit, which is the hexagon just drawn. Now, if we take another plane of hexagonally close-packed atoms and shift it to fit into the kind of void space, the little recess created by bringing 3 atoms together, say, for example, here, here, and here. So those little black spots, we're going to locate atoms in that little recess area to help anchor the next plane of hexagonally close-packed atoms. That'll give us the next layer. Okay, so it's been shifted laterally to position atoms into those recesses created by bringing 3 atoms together in the former plane. As we go to the next layer, we eclipse the first layer. So that is, this middle layer is eclipsing the outermost layer in this diagram. And then we have our completed sandwich, if you want, of 3 layers, 1, 2, and 3, with the top eclipsing the bottom and the middle being offset to position atoms into the recesses of the voids of the top and the bottommost layer of this 3-layer stack. By doing so, we create high coordination number. So we bring 12 atoms around a central atom in that regard. So the HCP structure has a coordination number of 12. And we get 6 atoms per unit cell. Quite high now, 6 atoms per unit cell. We're going to get 3 from within the structure, 3 in the center. We can see those in the middle structure here. 1, 2, 3. Notice that they're located within the hexagon. They're not cut by the planes or the edges of the unit cell. And we're going to get 2 half atoms at the faces. Okay, so we can see those here. That would be a half atom at the top and a half atom at the bottom. And now we have 12 corners in this hexagonal system. 1, 2, 3, 4, 5, 6, and 6 down below. And each corner is a 1/6 of an atom. Okay. So that gives us a total of 6 atoms for the unit cell, for the HCP unit cell. Okay. This will become a little bit more important when we discuss alloys and other structures, but we'll see that the size of the interstitial spaces, so these sort of corners that we haven't fully filled, triangular looking corners in 2 dimensions, but we'll see they're actually tetrahedral and octahedral in their definition, that these holes in the crystal structure and the size of those holes increases with the increasing coordination number of that site. Okay, so another way to show that, perhaps a little bit more clearly, is here. We showed that we were going to stack hexagonally close packed planes in a 3-layer sandwich to give us the unit cell structure for the HCP unit cell. The first plane eclipsed the second plane, so we could label that A for convenience, because those are twin sites. That is, there's a perfect positioning of the center of one of these atoms over top that, and all the way throughout the hexagon of the top and the bottommost planes here. So those eclipse each other perfectly. So we'll label those A planes. And in the middle, that has to be different because we've shifted it to accommodate and position atoms into sort of the correct pocket, where 3 atoms are from the previous layer are close packed. So you see that here, the B layer, the B plane of hexagonally close packed atoms, is shown as blue, and hopefully you can see that a little more clearly here, where that atom here resides on top of one of those near triangular looking holes from the first plane. Okay, so there's our middle layer. And in dark green is the bottom layer, and then kind of shown just as a lighter green for the top layer to represent the topmost hexagonally close packed layer. We have that. So hopefully that makes it very clear in a 2-dimensional projection that the top and the bottom layer are eclipsing one another, and the middle layer is offset to position those 3 atoms within completely the unit cell. Okay, very good. So in this unit cell, we've seen that we had to accommodate an extra layer within, so that means we've got to extend the dimension C to be beyond the other dimensions A here, which would be the hexagonal edge length A. So all these hexagon lengths would be A, and we've had to create space for the middle layer by extending and making that non-equivalent, and that final edge length is going to be C. So you can see the dimensions of C is about 63% larger than the A dimension to make room for that middle layer. It isn't double the distance to allow for an extra layer, but we take advantage of being able to put that blue layer on top of the void space in the previous layer, and that's what gives us a more modest number there. The face-centered cubic system that we've already seen is related to this hexagonal lattice by cutting the pattern in a different way. So if you look here, you can see here that this represents a cube, and that we've colored atoms within it according to hexagonally close packed layers. So cutting it on angle, diagonal through the cube, you can see here that we've got blue layers, green layers, red layers that are hexagonally close packed. And these take advantage of the same close packing that we've seen and have the same coordination number that we saw earlier. That is a coordination number of 12. In this case, we're going to shift the three layers in a different way from one another, and we won't see that eclipsing like we saw in the HCP. So we'll start with an A set of sites, and we'll put our first hexagonally close packed layer of atoms there. So A atoms are located there. And like we saw in HCP, we're going to take advantage of these sites for positioning the next set of atoms. So our next hexagonally close packed layer, B, is going to position on top of those sites. Okay, so we'll see that. That'll give us the B layer. Now that B layer has those same sites here, shown as C, and so we can put atoms there, and those can also be hexagonally close packed, and they are not going to eclipse atom site A. And so we'll end up with a pattern to those as being ABC. Okay, so you see that nice and clearly over here, where we've shifted the yellow layer from the blue layer by as much in a similar kind of way as we did the blue layer from the green layer, but not resulting in a eclipsing of the yellow layer onto the green layer. So this ABC stacking of hexagonally close packed planes of atoms gives us the FCC stacking sequence with the same coordination number 12 and high atom packing efficiency per volume. Okay, so to show that a little bit more clearly, here are those green atoms A. Here's a triangle that's a little reminiscent of the hexagonal packing kind of units that we saw, going from opposite corners within the face and down to the opposite corner across the unit cell. And so there's sort of a triangle of blue, if you want, and that is pretty indicative of our hexagonal close packing layer, as you can tell. And we're only getting one of the C atoms in this FCC lattice, and it's shown here at the frontmost corner. Okay, so C atom here is equivalent to the C layer here, and as we see, that C layer is shown there. Okay, so in the end, FCC is somewhat related to HCP in that we've got hexagonally close packed layers. However, they're offset in an ABC stacking sequence, whereas HCP is got an eclipse pattern in that A, B, A are the stacking sequences there for hexagonally close packed planes of atoms. Just another diagram here if you had trouble seeing that. Notice that our hexagonal close packed system with an A, B, A stacking sequence is shown at right, and that this is going to differ from what we see in the FCC cubic system. Our A plane this time is sort of on angle, our B plane on angle again, and our C plane is on angle again. And we fill space as efficiently, but inherit the cubic crystal system with an FCC Bravais lattice. Okay. There are many others that orthorhombics we didn't cover, tetragonal we didn't cover, rhombohedral, but many of the ones we did explain many of the atoms from the periodic table. So here's a sort of pictorial representation of that. We started with the simple cubic, the polonium, which was kind of an unusual crystal system. Only 52% space filling property there. And many elements at room temperature are liquids or gases, and so we kind of see that shown here. Many other solids can be explained by these crystal systems.